Okay, it is good to see everybody. Hope you're doing well. So the big announcement, of course, is okay. So the big announcement is tomorrow you have your second exam of the 9 weeks. In fact, a week from this Friday, next Friday is the end of the 9 weeks. So you definitely want to be thinking about not just this class, but your other classes, what your grades are, if you need to get anything taken care of. Remember, it's going to cover the 2 lessons over graphing the 6 trig functions and the lesson we were on previous to this, the sinusoidal applications. Okay, so hopefully everybody's already started filling out a note card. Whatever you think is going to be useful to you, you can go ahead and put on here. Does anybody need one? Okay, good, good, good. So that test is going to be tomorrow. When I came in today, I went ahead and got a few additional problems. So if you look at the first posting on our website, let me go ahead and click on this. I provided you several additional examples for the application problem. So just a little more practice in case you want it. The answers are in the same file. So if that helps you out, great. If you feel you're prepared, great too. Yeah. Oh yeah, all those are on there. Now, as far as the sinusoidal applications, though, those are pretty much sticking to sine and cosine. Yeah, yeah, yeah. But the other ones, I mean, they can ask you about characteristics of a particular graph. You won't actually be sketching because we did that on the previous quizzes. They are all multiple choice, but they are a college board. So, inverses will not be on the test. Okay, so what we're currently talking about is not on the test. In fact, my plan is to go ahead and give you the assignment for the inverse trig functions on uh, Friday of this week, and then that'll be due next Wednesday, and we'll go from there. We still have one additional lesson because we've been looking at sine inverse, cosine inverse, and tangent inverse, but I haven't shown you how to do the inverses of the remaining trig functions. That's what we're going to be doing for part of next week, and then we're going to start some identities. Okay, Mason. I do have a quiz plan next Thursday over inverse trig functions, but I'm going to carry that over to the second 9 weeks. So we're going to start with a grade, just hit the ground running. Okay. All right. Any other questions? Okay. Well, let's go ahead and get to it. So at this point in the notes, okay, this is what we should know about sine inverse, cosine inverse, and tangent inverse. So I've got all of these listed with the restrictions for the input ratios, and then the restrictions for what our angle answers are going to be. Also, we've got the quadrants that each one's going to be restricted to. And then, of course, over here, I've got the relationship between the 3 sides of the 2 special right triangles. So I thought it might not be a bad idea to go ahead and provide everybody with a copy of that. You keep it in your notes like a quick reference sheet, okay, to kind of help you out. Okay, so especially for those who weren't here yesterday, let's go ahead and do a little bit of review. Let's kind of lead up to what we're going to do today. So this is one of the papers you picked up on the way in. We have sine inverse of a negative root 3 over 2. Okay. Now, sine inverse can only be in what 2 quadrants? Okay, 1 and 4. So, Harrison, which one would this one be in? Oh, there we go. Remember, we choose the sign, or should we choose the quadrant based on the sign of my ratio? For sine inverse, positive ratios will go in quadrant 1, negative are going to go in quadrant 4. So I'm going to draw a triangle here. Okay, so this is the angle theta that I'm looking for. Remember, we're always rotating from standard position, that being the positive x-axis, to the hypotenuse of the triangle that I create. Okay. Now, with this being in quadrant 4 and the fact that I had to rotate clockwise, I at least know that my angle's got to be what? Positive or negative? It's got to be negative. It's got to be negative. We rotated clockwise into this. So let's go back to my ratio. This is going to provide me some sine lengths here. So we know that sine is always y over r. So I know this hypotenuse is 2. That's my radius. The height is a negative root 3. Okay. What would the other leg be? That would be 1. Yes. Okay, not a lot of people are taking me up on this today, but I'll ask several times. Anybody want me to run through Pythagorean theorem to show that that's the case? Okay, what type of triangle is this? This is a 30, 60, 90. Now, in fact, this angle that I'm looking for here, it would have to be 60. Why? There you go. Remember, the smallest angle in a triangle has to be across from the shortest side. 1 is smaller than a square root of 3. Okay, so I know my angle is 60. And remember, we already said it was negative. Bless you. So theta equals negative 60 degrees. But if you're working a problem where we have a special right triangle, I'd like my answer to be as a radian. So that's a negative what? Negative pi over 3. There we go. Okay. Question. Okay. Tangent inverse of square root of 3 over 3. Yeah, you're back. All right. Now, tangent inverse is going to be in the same quadrants as sine inverse, 1 and 4. But unlike sine inverse, remember, tangent inverse, we cannot include the y-axis. Remember, tangent is undefined at negative pi over 2 and pi over 2. Okay, that's why they're asymptotes. But even though knowing that, let's see. Where am I going to draw a triangle for this one? 1 or 4? This one's 1 because it's a positive ratio. Okay, so I'm going to go ahead and draw this. So this angle theta, that's what I'm looking for. That's my answer. Okay. What was tangent's ratio? I always forget. Y over x. Okay, so this is y, this is x. Okay, so I know that the height is square root of 3. I know that the base is 3. Can anybody tell me the hypotenuse? This is, well, it is square root of 12, but we can simplify that to square root of 3. Okay. Again, anybody want me to run through Pythagorean theorem? Okay. Well, what type of triangle is this? This is also a 30, 60, 90. So in this case here, the angle I need is 30. Okay, because the square root of 3 is smaller than 3. Okay, so that means my answer theta is going to be 30 degrees. As a radian, that's pi over 6. There we go. Now, both of these were 30, 60, 90 triangles, but they have different lengths. How's that possible? What's that, James? Different circles, okay, true. But what's the one concept I'm thinking about? I think, Drake, you said it? They're similar to each other. Remember, the side lengths are going to be in proportion. The corresponding angles are congruent. Okay, so I could take the values here, like in the first one, the 2, 1, and the negative root 3, and then I could go ahead and perform some operation on them, and I could go ahead and end up with the lengths of the other triangle. Okay, so similarity is what allows us to work with these trig functions. Okay, so that's what we're doing for the majority of the lesson. Now, yesterday, we just introduced the composition of functions. So that's what I want to work on today. I want to make sure that you feel really comfortable with that. So, I'm sorry. Oh, that's a question. So a composition of functions is just working one function right after the other, like back to back. The answer that you get for the first function, what we call the inside function, you're going to plug directly into the outside function. Okay, so let's go ahead and take a look at these, though, because these are going to show up occasionally today. We don't want to forget them. Let's say we are dealing with the unit circle where the radius is 1. Does anybody remember the 2 leg lengths for the 45, 45? Yeah, root 2 over 2, yes. So square root of 2 over 2, square root of 2 over 2. Good, 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 good. Okay, let's see here. Robbie, what was across from 30 in the 30, 60, 90? What fractional value? Not quite. Okay, what was that? 1/2. There you go. Now across from 60, that's where we're going to have square root of 3 over 2. There we go. Okay. So let's just go ahead and get right into the composition. Forget about the cosine inverse. We always start with the innermost function and we work our way out. See, that's why I've got two grids, because we're working two problems back to back. Okay, so I've got sine of pi over 3. Now, this is something that was happening yesterday. People were kind of confusing the rules we have for an inverse trig function with the normal trig function. Remember, they're going to be separate. Okay? What quadrant is pi over 3 in? 1. Okay? So let's remember how we'd evaluate one of these. So I'm going to first draw the angle. So let's say this right here is my terminal side. So this is pi over 3. Okay? Remember, we always start by drawing the angle. Okay? Now, that angle is going to become the hypotenuse of my triangle. I'm going to connect it perpendicular to the closest x-axis. Now, pi over 3, that is what? That is 60 degrees. Well, we just talked about this triangle here on the unit circle. So I know that the radius is 1. Across from 60 is square root of 3 over 2. And across from 30 is 1/2. Okay. Now remember, sine has a ratio of y divided by r. Well, we have an x, we got a y, we got an r. So y over r, well, the y value is square root of 3 over 2. That is a horrible 3. Let me try that again. Square root of 3. Third time's the charm. There we go. Square root of 3 over 1. So the sine of pi over 3 is the square root of 3 over 2. And we've seen that before many times evaluating a trig function, but this one's a composition, so we're only halfway done. Once you find the answer to that first function, the innermost one, this answer, this output, is now going to become the input for the next function. So the first answer is just going to plug directly into the next one. Yes?
So would you be able to say like inverse of cosine, or that function equals the inverse of cosine of root 3 over 2?
Yes. That's exactly what we're going to do. So now, that's why I've got this second grid. We want to evaluate cosine inverse of square root of 3 over 2. The answer for the inside function plugs directly into the outside function. And now we just have a second problem. Okay. Well, cosine inverse can only be in quadrants 1 and 2. Where's this one? Why 1? Because it's positive. So I'm going to draw a triangle here. Okay. Now remember, we rotate from standard position to the hypotenuse. So this angle theta, that should be my final answer. That's what I'm looking for. Okay. Well, what do we know about this triangle? Okay, yes. Because if I take this ratio, remember we have cosine inverse square root of 3 over 2. Cosine is always x over r. So in this triangle, I know the base has to be the square root of 3. I know the hypotenuse has to be 2. And we actually just saw this one. What would the height be? 1. So Peyton is absolutely right. This is another 30, 60, 90. Okay. So the one we're looking for, that angle has to be 30. Why is that 30 though instead of 60? It's across from the shortest side. So cosine inverse of sine of pi over 3, well, that's equal to 30 degrees, but that's pi over 6. That's what I want to focus on today. I want to look at compositions. Okay, working one function directly into a second function. Okay, bless you. Okay, so questions. Anybody confused? That's good. Okay, well, let's move on. Okay, so now we're on number 7. We worked number 6 yesterday. I believe that was our last problem. Is that right? Okay. So let's try this one. So with number 7, this is where it starts to change a little bit. So let's see what happens. We want to evaluate sine of cosine inverse of 5/13. Remember, we always start from the inside out. So forget about the sine. We're going to focus all of our attention on this cosine inverse of 5/13. Okay. Well, we actually just did a cosine inverse problem. Okay. This is positive, so what quadrant is that going to be? Right. So I'm going to label this. So this is cosine inverse of 5/13. So I'm going to draw a triangle right here in quadrant 1. I would rotate to the hypotenuse. So the first answer I'm looking for is that theta right there. Okay, well, let's see. Cosine is x over r. So I know this base would be 5. The hypotenuse is 13. So this is a triple, a Pythagorean triple. It'd be 5, 12, 13. Yes. Again, if you're not familiar with a lot of Pythagorean triples, they're just values that satisfy the Pythagorean theorem. You could still use the theorem itself. Did anybody want me to run through that? Okay. Well, now I've got all 3 side lengths. What's the problem? This is not a 30-60 or a 45-45. It is not a special right triangle. Okay. Now, here's the thing. It's almost like you got to take a leap of faith. The fact that we don't know what that angle is, I mean, we could use technology, we could break out the ruler and the protractor, sure, but it's not necessary. Even though I have no idea what that angle theta is, I'm going to be able to continue the problem. So let's just say cosine inverse of 5/13, it equals theta. Okay. But do we know anything about theta? Like being in quadrant 1, it's got to be what? It's definitely positive. And what type of angle would that be? Acute. It would have to be less than 90 degrees. That's absolutely right. Okay. Now, if I knew what that value was, to continue the problem, wouldn't I just plug it into the next function? Okay. Even if this is my situation, I have no clue what theta is. Oh, I could draw today. That would be fantastic. I'm still going to plug it into the next function. These problems can still be solved, even if I don't know what that first answer is. Okay. So let's take my information over here. Now I'm trying to evaluate sine at this positive angle theta. Okay. Well, let's do like we did a moment ago. It's a positive acute angle, so let's say it's in quadrant 1, so it's going to look like this. Okay. I'm going to use that angle, and I'm going to turn it into a right triangle. That's going to become the hypotenuse. Okay. We did this just a few moments ago. Okay. Here's what's going to allow us to solve these problems. What do we know for certain about these 2 triangles? They're always going to be what? They're always going to be similar. Now, for us to get around this problem and get a solution, if we don't know what the answer to the first function is, we're going to believe that the 2 triangles are identical. So I'm going to reproduce it. So I got a 5, I got a 12, I got a 13. Sine is y over r. Okay. So what's the y over the r? 12/13. That's the answer to your composition. And it takes some people a little while to kind of, wrap their head around that. It is okay if you don't know what that value is. You can still find the answer to the composition. Okay. Questions? Okay. All right. Well, let's look at this. Now, I'm just going to go ahead and mention this briefly. This was the first part of your packet that we looked at. Oh my gosh, was it last week? I think it was. And I said right now we're going to go ahead and skip it because we haven't gotten to compositions yet. Now, these are basically going to say that if you have this particular setup, it always has to be a trig function and its inverse. Okay, that whatever you start with is going to be your answer, but only if it falls into a certain restriction. So these are very specific cases. My opinion on this is they happen so rarely, I don't think it's worth memorizing these or even looking at these. That's my personal opinion. If you want to go ahead and look at those, I mean, you are more than welcome to. I would say just go ahead and solve the composition as 2 problems back to back like we've been doing. You're going to get your answer every time. Okay. So if you're interested in these and you want to take a look at them, or if you want to come in during tutorials and you're like, hey, why is some of these working and some of them are not? We can definitely take a look at that. Okay. But let's move now to see. This is right above number 6 on the same page that we were on. Okay. Now you'll notice I've got A and B marked off. We already solved those earlier in the packet, so there's no reason to do it again. So C says I want cosine inverse of cosine of a negative 1.1. Okay, so I'm going to go ahead and tell you those rules that we just looked at, they don't apply here. It doesn't fit this one. So the answer is not going to be negative 1.1. Okay, just kind of give you a heads up. Okay, so let's run through this. Where would I start? There we go. We're going to start with the inside trig function. So right now, let's pretend that cosine inverse doesn't exist. We want this one. Okay, so I'm looking at cosine of a negative 1.1. Now, that's not an inverse cosine. That's a normal everyday cosine. So that means that negative 1.1 is a what? That has to be an angle measure. Yes. So in this case, it's specifically a radian measure. How do I know that's a radian instead of a degree? It doesn't have the degree symbol. That's exactly right. Okay. So first thing, we've got to be able to sketch this. Okay, so it's been a while since we've seen these. So we have 0, negative pi over 2, negative pi, negative 3 pi over 2, all the way back around to a negative 2 pi. Okay. So can anybody tell me, what quadrant would that negative 1.1 radian fall into? So I've heard 2. It's not 2. What's that? It's not 3. 4. Okay, so I know this is kind of unusual because it's a decimal, so why don't we go ahead and convert the other measurements to decimals as well? Let's start with the easy one. Okay, what's pi? 3.14. So wouldn't negative pi be a negative 3.14? Yeah. Okay. Now, negative pi over 2, well, that's just half of negative pi. That's a pretty simple operation. So I'm going to get a negative 1.57. And when you think about it, what's half of 3? 1.5. Half of 0.14 would be 0.07. Hence why I got the negative 1.57. Okay. Well, let's see. Negative 1.1, would it be larger or smaller than that negative 3.14? Definitely larger. So that already eliminates quadrants 1 and 2. Okay. But how does the negative 1.1 compare to negative 1.57? It's larger, so that means quadrant 4. Okay. So is everybody okay with how I reasoned my way through that? Okay. So I'm going to go ahead and rotate clockwise. Let's say this is my terminal angle. So my angle here is 1.1 radians. Remember, we're not saying the angle itself is negative. The negative simply tells me the direction I have to rotate. Everybody's okay? All right. So I've got my angle. Okay. So I'm trying to evaluate cosine of this angle. So I'm going to turn this, just like we've done before, into a right triangle. So I'm going to connect it to my closest x-axis. Okay. What's the problem? This triangle is not what? It's not special. See, unless it's 30, 45, or 60, we don't immediately know what the side lengths are going to be. That's still okay. We know that we're going to have some x, we're going to have some y, and some radius r. You remember in the previous problem when we didn't know theta, and the problem turned out okay? We're not going to know this ratio, and it's going to turn out okay as well. Okay? So let's just say that cosine of a negative 1.1, let's just say it's whatever the x would be divided by the r. It's some ratio x over r. But what do we know about this? Should it be positive or should it be negative? It would be positive, because let's go back and see. Now, the radius is always what? Radius is always positive. Now, remember, we're in quadrant 4. What's the only value that's negative there? The y, so the x is positive. So whatever this fraction is, it's got to be positive. Now, this is another leap of faith. I have no idea what x over r is. Okay? But I'm still going to take it, and I'm going to plug it into the next function. So now I'm trying to evaluate cosine inverse of that x over r. This is perfectly fine. We don't need to know what that is to get my final answer. Okay. Now, what do you think? 1 or 2? Why 1? The ratio is positive. Okay, so I'm going to go ahead and draw a triangle right here. So this is when I would use these values to start filling in the sides. Well, if I have that exact same x and that exact same radius, wouldn't that give me that exact same y? And remember what we said a second ago anyway, for the first function, if you're not able to get an answer, what are we going to say about the two triangles? They are exactly the same. They're identical. Okay. So what would this angle be across from the y? 1.1. But isn't that the angle we're looking for when we rotate? So it's not negative, it's positive, but it's not the original input. How are we doing? Like I said, it's a little weird at first until you kind of get the idea. Okay. Is there anything I can help with? Okay. You like it though? Pretty exciting? I know. Don't get too excited. Compose yourself. Compose. Compositions. You know, I stick by that. I stick by that. Okay. Well, let's try some more. Now, this one right here, cosine inverse of sine of pi over 3, we actually worked that at the beginning of class today as our first review problem. I didn't realize I accidentally copied it until I went to the, after I got the copies back. Silly me. So we can forget that one. Let's go to sine of tangent inverse of 5/12. Okay. Sine of tangent inverse of 5/12. So we've done several of these compositions together so far. Let's try one on our own. Okay. I'm going to give you 2 minutes. Run through sine of tangent inverse of 5/12. See if you can give me my final answer. Okay. Here we go. Tangent is y over x. And then we'll talk about it. And we're at 12:04. Oh, we got almost 20 minutes. We got plenty of time. 50 seconds. $30 seconds. Mason, what do you think about that? That's pretty cool. Okay, here's what you should be getting. 5/13. Okay, how many folks got that? Nice. Okay, let's run through it just to be on the safe side. So we're starting with the innermost function. Tangent inverse of 5/12. Okay, 1 or 4? Okay, 1, it's positive. So I'm going to draw a triangle right here. Tangent is always y over x. So that means the height is 5, the base is 12. We just saw this triangle a few moments ago. 5/12, 13. Okay, so the answer to this one is that angle theta when I rotate to the hypotenuse. But this triangle is not special. Okay, so even though it's not, I'm going to take this positive acute angle theta, and I'm going to go ahead and plug it into the next function. Okay, so being positive and acute, that's going to put me in quadrant 1. So there's my angle theta. I'm going to use that to create a right triangle. Now, if we don't know what the answer to that inside function is, we're going to immediately say the two triangles are what? They are the same. So I'm going to reproduce this. Here's 5, here's 12, here's 13. Remember, sine of theta, this particular theta, we want the y value divided by r, so that's how I got 5/13. How are we doing? Good? Okay. All right. Let's try this next one. Cosine of cosine inverse of 2/9. Okay, so 2 minutes on the clock. Cosine of cosine inverse of 2/9. Excuse me. One minute. One 5 seconds. Okay, show of hands. Who believes they have the answer? Not a lot of hands. Or let me rephrase the question. Who believes they have an answer? They're just not sure if it's right. Okay, there we go. There we go. Mariana, what'd you get? 9/2? So close. Not quite. James? 2/9. This is one of those problems where the original input is the answer. This goes back to those rules I referenced, but again, they happen so rarely, I wouldn't even bother with them. Okay, how many folks got that right? See, now that's a lot of hands going up. Okay, let's run through it. So cosine inverse of 2/9 is my first problem. Cosine inverse of 2/9. Okay, well, because that's a positive, we're going in quadrant 1. Okay, so there is the angle theta that I'm looking for. Remember, cosine is x over r. So I know the base has to be 2. That hypotenuse would have to be 9. Now, finding that over the leg, you should have gotten the square root of 77. Does that look familiar? Okay. So once again, this triangle is not special. So I'm just going to say, okay, we've got this acute positive angle theta. Even though I don't know it, that's okay. I'm going to plug it into the next function. So now I have cosine of theta Okay, well, being positive and acute, let's say it makes me this angle. Using that angle, I'm going to create a right triangle. If I don't know that value, what do we know about these triangles? They're the same. So 2 square root of 77, 9. And cosine wants the x divided by the r, so that is how we got 2/9. Okay. Are we starting to feel a little better about these, even though that middle value, we have no clue what it is? Okay. All right, so how about this? The next one's going to be our last problem today, but at the end of 2 minutes, the wheel of destiny will choose a lucky person to come up and walk us through that. And I'll give you a heads up, the answer will not be 2 pi over 3. It will be something else. Okay, so 2 minutes. Try this one. Okay. I will go ahead and set up. Make sure we have enough numbers on wheel. We've got to go to 32 for this class. And right now we're at 30. Okay. Okay, so Dagan and Soren, we definitely don't want them to feel left out, so I'm going to get their numbers in there. Okay, let's give this a good shuffle. Okay. Okay, 1 minute. Ooh. Okay, 20 seconds. Okay, here we go. Who is our lucky contestant? Okay, 18, that is May. May is so happy she can't believe it. Okay. All right, May, you want to help us out with this one? You think you got it right? No? Okay, that's perfect reason to come on out. Okay. So first we need sine of 2 pi over 3. Now, while she's about to start, what do we notice about this composition? The triangles turned out to be what? They were special in this case, yes. So we actually should have found values. Okay, so hey, let's start with the sine of 2 pi over 3. That's in what quadrant? Not the first. Not the fourth. Second. There we go. So 2 pi over 3 is in, there we go. So here's what we got. So rotating from here over to here, that is the 2 pi over 3. Okay, so May, what would this reference angle be? How many more thirds would give me a whole pi? Pi over 3. Okay, but we know pi over 3 is, it's special. Pi over 3 is 60 degrees. Okay, so let's start to fill this in. We know that's 1. What was across from 60? over.
Two.
Okay, so let's write that. Yeah. So that's square root of 3 over 2. And what was the side length across from 30?
Wait. 1/2.
1/2. And then there's just one little detail, not super important. Remember, we're in quadrant 2, where x is negative. Okay. So now we've got, here's the y, here's the x, and here's the r. Sine wants y over r. So what would sine of 2 pi over 3 equal? Over 1/2? Over 1. So it would just be square root of 3 over 2. Where am I going to put that square root of 3 over 2? I'm going to take that answer, plug it into what? Remember, you just solved this one. So now I'm going to okay. So this is going to be sine inverse of what? What was it you just said? There you go. Okay, so the answer to the first function plugs directly into the second function. Okay? 1 or 4? 1, okay. So we're going to draw a triangle. Okay, so that'd be square root of 3 and 2. So what's this base length here? 1. Okay. Now, even though these two triangles have different lengths, this is also a what? It's special. Which one is it, 30-60 or 45-45? 30-60. So this is coming down to the last step. This angle right here, when I rotate, that's what I want. Would it be 30 or 60? Why? There we go. So sine inverse of sine of 2 pi over 3, what should it equal? 60 degrees. But what is that as a radian? There you go. Good job. Okay, how many folks got pi over 3? Good, 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 good. Okay, just like anything else, it takes a little bit of practice. Good job. Okay, so we're going to go ahead and call it quits right there. Okay. Remember, will this material be on the test tomorrow? No, 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 no.